Welcome to this first introductory chapter of Fundamentals of Energy Storage Technologies. We'll first have a look into the origin of energy storage, and here we will see that humanity and the whole ecosystem basically relies on storage, if you notice it actively or not. So the largest share of energy before industrialization was actually stored solar energy in biomass. And you can readily see this by just looking at nature. You will see trees and you will see grass, any kind of plants. This is all what you consider solar energy saved in biomass. And how did this accumulate? Well, the first kind of storage mechanism for energy storage is so-called photosynthesis. Photosynthesis cuts basically into two steps. You have the so-called assimilation as the first step. In the assimilation process, you convert this solar energy, what I just talked about, together with water and carbon dioxide into, for example, glucose in the form of energy storage. This is C6H12O6. And from this, you will yield oxygen as a kind of waste product for the plants. So what we're doing is we're converting the solar energy into kind of sugars, into biomass. And here you again see the chemical formula. So we're basically using carbon dioxide and water together with energy from the sun in this case to produce this kind of glucose here together with oxygen. Now we converted the energy from solar energy into basically chemical energy here in the form of biomass. And the sign of energy storage is that, of course, you just store this energy. At some point, you want to get it back. And this is what the reverse process is. This is the so-called dissimilation, or you can also commonly call it a simple combustion. So what we're doing is we're taking oxygen from outside sources, and we are using this oxygen together with this energy storage to yield back basically water and carbon dioxide together with energy. And here again, you see the chemical formula. So here we're using glucose together with oxygen to obtain carbon dioxide, water, and energy out of this equation. So basically, we used this molecule C6H12O6 as an energy storage to first save energy in the assimilation and then release the energy in the dissimilation. And you will readily see that we as humans are usually on this dissimilation process side here. So we are eating this kind of sugars here, and we are breathing oxygen to convert these into energy from which our bodies can function. Now, photosynthesis allows to store radiation energy in the form of chemical bond energy by creating these molecules. However, the photosynthesis efficiency depends a lot on how much energy can actually be absorbed, and this depends a lot on the individual plant type. Theoretically, plants are able, on a molecular level, to obtain a theoretical efficiency of 13%. This means 13% of the radiation energy from the sun can be converted into chemical bond energy. However, what you usually observe is that the real efficiency falls short of the theoretical value. This is due to processes called downshifting of photons. So we need photons of a certain energy to be used in these processes. Also self-sustain and other processes. So self-sustain here means that the plant, of course, does not permanently just convert solar energy into chemical energy, but the plant also has to gain energy from something, so it also does some of these dissimilation processes itself. Now, accounting for all losses, the actual net primary production or NPP efficiency of photosynthesis is around 0.5 to 2.5% only, which is a very low kind of efficiency for this kind of storage process. So you can imagine when your global solar radiation energy can be represented by this kind of bar, you will lose approximately half of it already just to optical losses. You will then have further losses due to orientation and inclination of your surface. You will have some reaction losses due to the chemical reactions, and also you will have a certain amount of respiration. So this is again this self-sustained part of the plant. And you will basically end up with this little proportion of the global solar radiation, which is actually usable for plants. Looking at fossil energy sources, you readily know that basically fossil energy sources have been important for the last years and even for the last decades. So since the Industrial Revolution, fossil energy sources are actually gaining in importance increasingly. So what are fossil energy sources? These are, for example, coal, oil, and gas. The important thing to notice about coal, oil, and gas is that they are formed over millions of years via biochemical and geochemical reactions. This is because they often require either very long time, or they require specific pressures and temperatures. The most common fossil energy sources I've listed here, this is, for example, brown coal, or so-called lignite, which originates from dead organic biomass accumulated in anaerobic conditions under high pressure and temperature in geological timescales again. Black coal, or so-called hard coal, is formed when the brown coal has a higher energy density. So the brown coal is again pressed even more. It will convert eventually to black coal. We have oil. Oil originates from dead plants and animal biomass, which accumulates, for example, on the ocean floor. Then subduction due to continental drift on the Earth exposes the material again to very high temperature and pressure and transforms it into oil. And natural gas as such is formed in a similar way to oil, and actually it's even found as an associated gas when oil is mined. Now, how can you imagine this to happen? Basically, here I have a visualization of what I just explained you. We do have, for example, animals, plants, and others, and these will, for example, be subject to biological decomposition. This biological material will then be covered under more and more of these sediment layers, and the sheer weight of that will exert more and more pressure on them. So, for example, from swamp and peat, you will create lignite just from this biomass, which is on the floor and will be covered by more and more layers. And the lignite being exposed to high pressure and temperature will again convert into the more dense variant, which is black coal. The same thing you observe on the ocean floor, where, for example, rests of plankton or of ocean plants or fish will sink to the ground and then sink further into the ground, being covered by more and more sediment, eventually forming, for example, natural gas or forming crude oil. The main issue I would like to point out for you here is the issue of time scale of formation. It is important to realize at this point that to create these fossil fuels, it takes millions of years. However, if we simply think about burning coal or burning natural gas or using crude oil, we are thinking about a consumption which, in contrast, happens more or less instantly. Now, fossil fuels are actually a natural part of the so-called carbon cycle, and this is something I would like to introduce you to now. The so-called carbon cycle is a closed cycle between CO2 and oxygen, consisting of producers, consumers, and decomposers. This kind of cycle, because it's closed, means it's self-regulatory. So if one of the components increases, the other will also increase, and it will self-regulate the system. So there can never be a disbalance in the system. So I've told you that there are producers, consumers, and decomposers. So how does this all go together? We have producers. These are so-called plants, simply. Plants are an example for this. plants use solar energy to convert carbon dioxide and water into biomass. This is, we have a certain atmospheric carbon dioxide here, and plants use this assimilation process to convert this CO2 together with solar energy into biomass. Then we have the group of the consumers. Consumers can, for example, be people, us as humans, it can be animals, and it can be other plants, for example. They use oxygen to oxidize this biomass and yield energy from it. This is the process we've discussed earlier, which is the so-called dissimilation or combustion process. And we have the so-called group of the decomposers, which are soil organisms usually, and they can aerobically degrade biomass and return carbon dioxide to the atmosphere. So you already see here that we have kind of a cycle. We have atmospheric CO2, we have plants which will use this carbon dioxide and create biomass from it. And we have this group of consumers and decomposers, which will basically utilize this material to get energy from it and return carbon dioxide back to the atmosphere. Now, the situation is a little bit more complex because we also have the oceans in this whole equation. The ocean has a lot of carbon bound via photosynthesis as well, for example, in algae, in phytoplankton, and in corals. And this originates based on the fact that CO2 is actually very water soluble. So you can basically store carbon dioxide in water. And this is the reason why the ocean actually absorbs a lot of carbon dioxide from the atmosphere and why our oceans contain 50 times more carbon dioxide than the atmosphere. However, don't be mistaken here. In the ocean, you will not find great amounts of the gas itself, but rather you will find chemical derivatives from it. So the so-called carbonates, CO3 2- or bicarbonates, HCO3-. And now you will see that the cycle kind of extends here. So we will dissolve our CO2 in the ocean. It will be utilized, for example, by aquatic bacteria or by aquatic plants. And we are extending our cycle basically for this ecosystem of the ocean. Now, how do fossil fuels fit in all of this in this scheme? So fossil fuels, so-called hydrocarbons, are can be combusted. Combustion of fossil fuels releases CO2 in the atmosphere. And this is exactly what you see here. We have, for example, factories creating CO2 by combustion of these fossil fuels. The problem here again is that the carbon dioxide released into the atmosphere happens more or less instantly compared to geological timescales, and the fact that the biomass and the ocean absorption of CO2 takes several centuries to convert this kind of biomass into fossil fuels. And this yields to a net rise in atmospheric CO2 levels because simply all of these dissolution processes here and this conversion processes into new fossil fuels, as well as this assimilation from plants, cannot happen fast enough to keep up with this huge amount of carbon dioxide released through the combustion of these fossil fuels. So this is the key aspect you should take away here in this chapter of the carbon cycle. Fossil fuels itself are nothing bad. The issue is just that the production of these fossil fuels takes millions of years, and we will combust them more or less in a comparably in an instant. And this leads to a disbalance in this self-regulatory cycle, simply because we cannot regulate it fast enough to keep up with the huge release of carbon dioxide into the atmosphere. Why do we actually need storage? This is something which mostly arises with the outcome of transportation and with the outcome of renewable energies. And it is important to note here that renewable energies alone do not work adequately without storage. So why is that? That is because the feed specifically from wind and photovoltaic, for example, is subject to limited predictability. So you cannot determine when there will be clouds. You cannot determine when there will be strong winds, at least not with sufficient reliability. And this is something you're seeing down here in this graph, which shows you on different days the amount of production which you have from solar here displayed in orange and from wind energy shown in blue. And by this, you see that you do have fluctuations over the day for solar energy, which is, of course, the day-night cycle. But you can also never really determine the absolute amount, the peak amount, which you will get. Same goes for the wind. For the wind, you have even more fluctuations, as you can see here. And the key thing, what storage technology should provide, is a smoothing of these fluctuations. And the goal of all of this is to minimize the so-called curtailment. Curtailment meaning the more or less cut off of renewable energies just because we cannot use the surplus which we generate simply because there is no demand for this energy during a specific time. Now, these storage technologies should therefore ensure a balance between the demand and the supply at all times within and also across the borders of a market area. And for this, I would like to introduce into the concept of residual load. Residual load is defined as the power needed, so that's defining the demand, and the feed-in of renewable energies. This is our supply, basically. And you will readily see in this equation that if our power needed is smaller than our feed of renewable energies, we will get a negative value. And this means that we have a negative residual load, and this implies that we do have a surplus of energy. Same goes in the other direction. If our power needed, if our demand is bigger than our feed-in of renewable energies, our supply, we talk about a shortage, and this is a positive residual load. Let's visualize this in another way. Let's say this is our power needed here, then our renewable feed is smaller, just like this. You will have a residual load of this much. On the other hand, if our power needed is only this much and our renewable feed generates that much energy here, we do have this kind of negative residual load, which we cannot utilize in this specific time. So what do we do in the individual situations? If you have a positive residual load, so you have a lack of energy, basically, you have certain kind of options if you're a grid operator. So you can ramp up dispatchable power plants. So you can start gas turbines, for example. Another reaction might be to reduce the load with demand response. What does demand response mean? Demand response means that you will approach big consumers, so typically industry consumers, and you will pay them to reduce their energy consumption during a specific time, so they don't use so much energy from the grid. Another option, of course, is to import electricity outside of your own grid. And the option which is mostly related to this kind of course here is you can discharge stored energy if you have any. Now, the other side, when you have an excess residual load, so a negative residual load, meaning a surplus of energy, you can increase load with responsive demand. So this means, for example, you're making your energy cheaper, so people would like to consume more. Thereby, you can reduce this residual load here, or you can export electricity simply because you have too much. The option related to this course would be to use this time to charge storage systems and utilize this electrical energy storage to store a certain amount of energy to then discharge it when you have a positive residual load. So from this kind of situation, there arises a certain demand of electrical energy storage. And this electrical energy storage, as you can see here, would help to balance the fluctuations in the generation. And these fluctuations are simply a result of surplus and of shortages at different times. And you will always have a fluctuating residual load here. And storage technologies are meant to be used when all primary balancing and flexibility options are basically exhausted. And these primary balancing and flexibility options are the ones I discussed here in always the first parts of the reaction section. To properly understand energy storage, we have to think about a few key definitions here. So energy storage in an energy technology facility for storing energy is usually done in the form of internal potential or kinetic energy. And any energy storage system performs usually three processes. So we have a so-called charging process, also called a loading process, a storing process, also called holding process, and we have to discharge the energy, which is the so-called unloading. This is what you see visualized here. So we have a certain amount of energy, which is our energy in our system. We charge up some kind of energy storage. We store this kind of energy in this kind of storage container, more or less, which doesn't have to be a physical container. And then we discharge it again to get energy out of it. Now, let me note a key point here. Each of these processes here, so the charging as well as the storage for a certain amount of time, as well as the discharge, are subject to efficiencies. This is described here by this eta charge, eta storage, and eta discharge. This means that not all the energy I put in the process can be efficiently converted into storage, into stored energy in this case. So the charging process will have some kind of losses. The storage over a prolonged amount of time will also be subject to certain losses, and getting the energy back into our usable energy will also be subject to discharge losses. Let me make one thing very clear here. In the course of this, chapter, in the course of the other sections, I will sometimes talk about losses. You might know from thermodynamics that energy can actually never be lost. So whenever we talk about losses for energy storage, we're talking about the irreversible loss of energy for our storage process here. And this basically means simply that when we have electrical energy, not all of this electrical energy can be yielded back as electrical energy, but we will convert some part of this energy into non-usable energy. For example, heat energy. And you can readily see this, for example, when you use electric device, they will heat up, and you would call this, you dissipate energy in the form of heat energy. And of course, this kind of heat is in this case a non-usable form of energy. So you would consider this as an energetic loss. Energy storage systems can be distinguished regarding their rechargeability. They are so-called primary energy storage systems. These are energy storage systems which can be charged and discharged only one time. A typical example for this are solid, liquid, and gaseous fuels. So like gasoline, once you burn gasoline in your car, you will not be able to recharge it, except, fueling new gasoline into your car, basically. And also another common example, also called disposable batteries. So these batteries which come charged, you simply discharge them one time and then you recycle them. And the second sector are the so-called secondary energy storage systems. These are energy storage systems that can be charged and discharged multiple times. Of course, this is maybe the more interesting field here, especially when we're talking about sustainable energy storage. We want a system that can be utilized multiple times. A typical example for this are capacitors, flywheels, compressed air storage, or secondary so-called rechargeable batteries, like, for example, lithium-ion batteries. Please don't worry if you don't know some of these technologies yet, like flywheel or compressed air storage. We will cover all of this in greater detail in the respective chapters. Before, we should look at the certain sectors of energy storage systems. There is something called sectoral energy storage systems, and this describes the concept that a sector stores energy only within its own sector. We've already heard that energy storage does not necessarily have to mean electrical energy storage. We can also store kinetic energy. We can store potential energy. So we can also store heat energy, which would be a representative of kinetic energy, for example. So looking at the power sector, so for example, a nuclear power plant or a hydro facility, we are converting power to some other kind of storage. So this process would be called power to X. We store this X, and then in a consecutive process, we discharge it by getting power back from this X. So the key thing to take away here is that you convert power to some storage, and then you get power back exactly from the storage. So from power, you get power. Another example for this is the transport sector and the gas sector. So you can, for example, have crude oil and or biomass. You can convert this biomass to X, so again to some kind of storage, and you can store this X. On the other hand, you can take crude oil and simply store it in a tank. And then in the discharge process, you can then discharge this kind of crude oil or biomass to shaft power. So this would be a utilization into the transport sector if we see these kind of sectors here as one. And lastly, we have the heat sector. So the heat sector would also describe conversion of heat to some kind of storage way X, and then from X we get back to heat. So now you will say, okay, if we have sectoral energy storages which feed themselves, there should also be something feeding another sector. This is called cross-sectoral energy storage systems, and they are used to feed their energy into other sectors. So they allow for the charging and discharging into different sectors, and this is what we call sector coupling. Let's take the example that we have an excess of energy in our power sector, and we want to store this somehow. What we could do, instead of just converting it to some X and then getting power back, is we can use this electrical energy here to power a heating rod. For example, in an electric kettle. So you can store your energy in water and then get your energy back as heat energy for the heat sector. Another way of doing this would be to provide a charging process like power to gas. So you kind of create gas from this excess power, and we will later have a look in how this works. You can store this gas, and then you can use a gas boiler to feed energy into the heat sector. Another sector which you could feed from the power sector would, for example, be the power sector. So you can use your power to convert to gas, similar to this process we've looked at here. You can store this gas, and then you can use this gas, for example, in a vehicle to provide energy for the transport sector. Energy storage systems can be classified in multiple categories. Most typical characterizations and classifications include the physical classification, energetical, temporal, spatial, and economic classification. The typical classification in terms of physical type is that we have electrical, chemical, and electrochemical energy storages, mechanical and thermal energy storage. Regarding energetics, we can either talk about power energy storage or energy storage itself. We can have a look at temporal storages, so the time span over which we store the energy. Is it short term, is it mid-term, or long-term storage? Also, where is the storage facility provided and how it's organized? Is it a central one? Is it a decentral one? Is it stationary, or is it maybe even a mobile energy storage? And we can have a look into different markets. So for different markets, different energy storage systems are more interesting. We can have a look at the capital cost of the individual energy storage systems and their operating costs. While I will cover all of the respective topics when we talk about the individual storage technology, I will classify the energy storages first of all in this physical distinction here. So we will talk about electrical energy, including electrical power, as well as electrostatic or electromagnetic energy. Chemical energy includes, for example, molecular binding energy of chemical molecules. The mechanical energy is usually kinetic or potential energy, and the thermal energy can be used, for example, for heating and cooling. Now let's go through all of these different storage technologies, and I will tell you a little bit about them before we dive deeper into them in the respective chapter. So electrical energy storage systems are storage systems which save your energy or which store your energy in electrostatic fields, for example, in capacitors, or in magnetic fields, so-called superconducting coils. It is important to note here that these kind of storage systems are exclusively secondary energy storage systems. So they are always rechargeable. So you can always charge and discharge them multiple times. The electricity can either be saved as direct current, and it can be stored electrostatically in capacitors, or it can also be stored as alternating current. So it can also be stored in electromagnetic fields using coils or inductors to make it more general. To minimize losses, these electromagnetic energy storages rely on superconductors, and they are also named accordingly. So, for example, the superconducting magnetic energy storage, or so-called SMES, is using these superconductors to store electricity as alternating as an alternating current. In this course, we will mostly focus on capacitors and related systems such as supercapacitors because they are the more common energy storage system. Chemical storage systems store energy in terms of a high energy density energy carrier. This might sound very abstract, but it's actually something very simple. We're looking here at hydrogen, at natural gas, at biogas, methanol, gasoline. So we're looking at some kind of molecules which we can generally say combust in one or the other way. So charging works as in a natural way, for example, photosynthesis, or in an artificial way. So for example, power to fuel or the power to gas, what you already heard about. The storage of these chemical energy carriers can usually be done in tanks or in caverns, and they can be discharged typically by combustion and by conversion of thermal into mechanical or electric energy. Notice here that this combustion always have an extra step. Usually you combust it, you get thermal energy, and this thermal energy you then convert into mechanical or electrical energy if you think about a car. However, hydrogen, for example, is an exception here because the hydrogen can be converted directly into electric energy using fuel cells. This is something we will also cover later when we are in the chapter of chemical storage. The focus in this course here will be on hydrogen, on methane, and on methanol production. Mechanical storage systems usually use gaseous, liquid, or solid media. And while this might be hard to imagine how you store it mechanically, basically the energy here is stored either in a positional kind of energy, so which is basically potential energy. It can be stored as speed, so basically kinetic energy, or as a thermodynamic state, which is basically pressure. Typical examples of this include compressed air energy storage systems, or CAES systems, which would be an example of this thermodynamic state or basically pressure. We have pumped storage plants, which would be an example of positional storage using potential energy. And we have the example of flywheels, which would be an example of kinetic energy storage. The focus in this chapter later on will be on this compressed air energy storage, on liquid air energy storage, so-called LAES. We will also talk about pumped storage plants and about flywheels. Thermal storage systems are also exclusively secondary energy storage systems. So these kind of storage systems can be categorized into three main subcategories. There's this category called sensible heat storage. Sensible heat storage stores energy by changing the temperature of a medium before and after charging. So this is something not very complicated. You can just imagine you have a certain amount of water, you heat this water in an electric kettle, and you have hotter water afterwards. So you increased the temperature, and therefore you stored energy in this kind of water. So to be more particular, you basically stored electrical energy coming from the outlet into heat energy, into thermal energy. And in this case, the mass and the so-called heat capacity determines the amount of the stored energy. Don't worry if this is not all clear right now. We will cover all of this in more detail. And as I already said, like you will have your hot water in a kettle, for example, and you might want to store this in a hot water tank if you really want to use it for storage purposes. And it becomes obvious pretty quickly that thermal insulation is something very vital, because once your water cools down, you will lose energy, or simply you will dissipate energy to the surrounding, and this kind of heat energy will not be usable anymore. There's another class called the latent heat storage, and this describes stored energy without the medium changing temperature, but only the state of the medium. And this is, for example, used in latent heat storages in buildings to mitigate temperature swings. How can you imagine this? Well, it is a physical concept that phase transitions require energy. So what does phase transition here mean? Phase transition basically means you make liquid water into gaseous water, into steam. And this process of converting liquid water into steam takes way more energy than actually just heating water for a few degrees takes. We will also have a greater look into this to make this a bit more obvious. And we have the so-called thermochemical heat storage, which is based on thermo-reversible chemical reactions. For this, you have to understand that any chemical reaction taking place is either associated with an energy release or it requires an energy intake. If we have a so-called endothermic reaction, that means if two chemicals react, they absorb energy, usually as ambient thermal energy from the environment. And this would be a typical charging process. So we're taking energy from the outside and charging it. And we have something called an exothermic reaction, which means that energy is released, that energy is discharged. And this would therefore be our second step in this storage procedure. So first of all, we invest energy to charge our storage as a chemical reaction, and then in the second step we let these chemicals react and we yield this energy back in an exothermic reaction. In the electrochemical energy storage systems, they are kind of related to chemical energy storage, although they have clearly different characteristics. So here we have the class of batteries and accumulators where energy is basically also stored chemically in the electrode materials. These kind of storage systems are categorized into primary and secondary energy storage systems. So they can either be single-use batteries, as we've already heard, or secondary batteries, which would be rechargeable ones. There's another class called the so-called redox flow batteries. Here energy is stored not in the electrode materials themselves, but actually in the charge carriers. The focus for this course will mainly be on the so-called lead-acid batteries and on lithium-ion batteries. For all of these energy storage systems, it's important to realize that the application defines your storage system requirements. So we've seen that there are physical, energetical, temporal, spatial, and economical reasons to prefer one or the other storage system. And therefore, you always have to decide your storage system from the application side. There are a variety of key characterization parameters which I would like to introduce you to now, which we will discuss at various points within this course. The first parameter is the so-called discharging power, measured in watts. So this basically represents the loading and unloading power as an energy per unit of time. So basically with this, you're thinking about how quickly you can load and unload your energy into your storage, and therefore also how convenient it is to use. So the power here, for example, would decide how quickly you can charge your phone and how quickly you could discharge it in your car to have faster acceleration or things like this. Then we do have something like the so-called power density. This is a typical way of how these values are given. They are given as a density value, so more or less as a normalized value per unit mass or per unit volume. This basically simply helps to account for the weight of energy storage, or more notably for the volume of energy storage, which is needed to obtain a certain amount of usable power. Then we do have the energy itself. The energy itself is the usable energy content of a storage system. So simply how much energy you can store. Note the difference here, please. Energy is generally how much energy you can save, and power tells you how quickly you can load and unload this energy. Energy is also often given as this normalized value to unit per unit mass or per unit volume. Then we have the so-called discharging and charging efficiency. This is something I already introduced shortly. So this is the efficiency of the charging and discharging process, most notably actually the energy conversion process in this regard. And we have something called the storage efficiency. So this is the efficiency of the storage process itself. So think about the fact that you have a kettle with hot water and you leave it for a day without proper thermal insulation, you will have your water be back at room temperature. So you basically dissipated all your usable energy as a non-usable energy, and therefore here your efficiency would be very, very low because you cannot regain any of this energy from your water because it's cold now. Then we have something called the self-discharge rate, which is mostly interesting for batteries. So self-discharge means that a proportion of the stored energy is basically lost due to internal reactions, for example. And we have the so-called discharging duration. This is a measure for how long it takes you to discharge or to charge your energy storage. Most notably in this course, I will often focus on the energy density here as a means of generally how much energy I can store per kilogram or per cubic meter, or generally per unit of mass and per unit of volume. What you can see here now is exactly this energy density, what I've just talked about. The energy density is given on the x-axis here in kilowatt hours per cubic meter. Please don't pay so much attention to the absolute value. Basically, I just want to give you an overview how the energy density is significantly different depending on your storage technology, and even within this storage technology, it can be very much different depending on the way how you store your energy. So first of all, looking at electric energy storage systems and, for example, mechanical storage systems shown in green and blue here, respectively, you will see that the energy densities are very low. Also, for electrochemical storage systems as well as thermal storage, you still have somewhat low values, especially if you compare it to chemical storage systems, most notably gasoline, with the highest energy density by far in this kind of comparison here. And this is a reason for the great success stories of fossil fuels, of course, because they have such a high energy density. And therefore, you can yield a lot of energy from them while they can be stored in very small volumes. Now, it is important to have a look into this temporal classification as well, which I noted earlier. The temporal classification usually rates storage durations either as short-term storage, so where you're storing your energy just over a few seconds to days, and long-term storage, which basically refers to weekly, seasonal, or sometimes even yearly storage. The important parameter here is the so-called discharge duration, also termed the E to P, the energy to power ratio. And this is also how this is calculated. So your discharge duration, basically a time, is given as the energy of charge discharge divided by the power of the charge in discharge. So what this equation basically gives you is you have a time here, you have the amount of stored energy here, and you divide it by how quickly you can charge or discharge this stored energy. And this, of course, will give you a time. If you compare this to general physics, like from mechanics, you will see that this is basically time equals distance divided by speed. And this is kind of something similar what we have here. Just instead of distance, we have our energy, and instead of speed, we have basically our power, which is a discharge speed or charge speed. And based on this value, we typically say that a short-term storage has an E to P ratio of 1 to 10 hours. So it takes you 1 to 10 hours to charge or discharge your energy storage. And these kind of storage technologies usually aim at a high cycle numbers and high efficiencies. What is a cycle? A cycle basically means I have an energy storage, I charge it, I store it maybe for a certain amount of time, and I discharge it. This is regarded a cycle. So these kind of short-term storages are basically used to balance short-term fluctuations in the electric grid. And you readily see when we talk about short-term fluctuations, we should have relatively fast charge-discharge times. So the long-term storage systems usually have an E to P ratio of much more than 24 hours. So we aim at high storage capacities here. So our E is very big, and we typically aim at a low storage loss, and a low cycle number, and efficiency is usually easier to compensate. And you can easily imagine this by saying you maybe charge a storage and you hold it for half a year. Then this storage loss here is much more relevant than if most of the time you're simply charging and discharging. So here we mostly aim at having low storage losses. And these long-term storages are typically used to balance seasonal fluctuations in energy supply. The time over which the energy can be stored most efficiently with the corresponding technology is shown here. And this is also something which varies significantly, not just with the physical method of how you store your energy, but also by the individual technology. For example, electrical energy storage with capacitors or with these inductors is usually something used for storage in the time scale of seconds. Also, flywheels as mechanical energy storage can be used in this second related energy storage. Batteries, in comparison, are usually used to store energy from even seconds up to days, sometimes even weeks. And this is also some area which usually this compressed air energy storage systems or pumped storage cover. Pumped storage, however, can usually even yield up to weeks or sometimes even months of energy storage, although higher ones are not so typical, as you can see. And the most long-term energy storage is usually found in the thermal energy storage, for example, in the form of sensible heat storage or in the form of CTES, so-called cavern thermal energy storages. In this final graph here, you see a comparison of putting all of this information now together. So you'll see the storage capacity here. So basically the energy you typically store with this kind of technologies and the discharge time. And the main point I want to make here is that there is no best storage technology, but it always depends on the application. So when thinking about which energy storage technology is the most suitable for you, you have to think about what kind of application am I aiming for? Do I need to charge and discharge my storage very often? Do I need a high storage efficiency, or do I need maybe a high charge and discharge efficiency? How long I want to hold this energy and how much energy I want to store? And depending on these parameters, typically for low storage capacities and low discharging times, flywheels and capacitors are the typical kind of energy storage. Going up to higher storage capacities and a little bit longer discharge times, we find the batteries. And if we increase our storage capacity further and we increase our discharge time, we usually end up at compressed air storage, pumped storage, hydrogen, which is, for example, generated by power to gas facilities, or methane, also being produced by power to gas. And this is, as I said, the key takeaway from this kind of introductory lecture, that you will not be able to define a best storage technology. It always depends on your individual application, which kind of storage technology is the most suitable for your purpose. Lastly, I would also like to have a look at the economic classification. So depending on your application area, energy storages are also subject to vastly different economic situations, depending on how big your application is or what you can afford for the given application to invest. I just want to give you a short idea here about how this is put to numbers. So you have one investment, which is the so-called capital cost, or CAPEX, capital expenditure. And this value describes the one-time cost incurred by a storage system, construction or startup. So this might sound a bit complicated, but this is basically just your initial building costs or buying costs for your given energy storage. But please note that you can have huge variations depending on the systems. Of course, a small battery is much cheaper than building a large-scale facility to pump like a water pumping system to store potential energy or something like this. So this capital cost of material storage is usually given as an energy capacity, and this is again given by the unit of dollars per kilowatt hours. Despite this normalization per kilowatt hour, the systems are still hugely different, just depending on material costs and efforts, of course. The second big cost part is so-called operating costs, or OPEX, the operational expenditure. And this results from operating a storage system, including, for example, costs for personal maintenance, insurance, and also variable costs, for example, for electricity, fuel, and replacement costs. Again, it is clear here that, for example, a big dam or storage facility for thermal storage requires totally different operational expenditures than, for example, a battery in your phone requires, which you just have to, where you just have variable cost in terms of electricity. Usually, this operating cost resembles around 1 to 5%, typically 2% of the investment cost.